So we found that in order to get the effect phi 1 to a point, a disturbance at one point in space-time, we needed what we called, I think we called it G prime of K function, which we broke up into two terms, right? So we had an a squared minus b squared like quantity, and so we broke it up into a plus b, a minus b, and that looks like k squared. Let's make it vector. These are the three components of the four vector k, the spatial parts, plus m squared square root. We had the minus I epsilon, right? We're trying to avoid the singularity or circumventing the singularity by adding this term, moving slightly away in the complex plane. Minus E, which is really, we should write this as K naught. This is, or K zero, the zeroth component of the four vector Ka. But we'll just write it as E. Minus 1 over, same thing there, K squared plus M squared square root minus I epsilon plus E. And then we have a 1 over 2b, which b in this case is the square root of K squared plus M squared. Okay, so this is what we need in order to find phi 1. So maybe we can write what phi 1 is in terms of G prime of K. It's really, what we found is that we need, as we make epsilon go to 0, we get the G prime that we cared about. So epsilon goes to 0, minus infinity plus infinity, d4k, so we're integrating all k values, all of the components of k. So we have 2 pi to the 4th, and of course they're related by the energy condition, e to the I. Here's the 4 vector k, space-time points xa and xa prime. We got rid of the x naught and replaced it with a prime. Makes for cleaner notation, and this is where this thing comes in, G prime of K. So that's our project, and this therefore leads to this limit as this quantity goes to 0 of, let's see, we have, let's pull out 1 over 2 square root of K squared plus M squared times the integral well, maybe I'm pulling this out of both terms, so maybe I need another bracket here. I want to make a mess of this notation, but so let's just write d4k over 2 pi to the 4th, e to the I ka, xa minus xa prime over. So we're just writing this. We're just putting this into here, and so that gives us k squared plus m squared square root minus I epsilon plus, sorry, this is on the minus e, minus e, minus 1 over 2 square root of k squared plus m squared times the integral. Here we have minus infinity, infinity. Well, we should really write multiple integrals, but whatever. D4k over, same thing here, 2 pi to the 4th. We're just reproducing these parts, e to the I k a xa minus xa prime divided by the square root part minus I epsilon plus e. So this becomes k squared plus m squared. And then we'll close this off. I don't have enough space. That gets closed off. And that's the integral that we have to evaluate. So this clearly involves the complex plane, because we have shifted this away from the singularity on the complex, on the imaginary axis. So there's the I, and we know how to do that integral. We're not going to go through the details, but this is basically the limit as epsilon goes to 0. This integral has been evaluated of dx e to the minus I xt over x, but we are adding this shift in the complex plane that allows us to avoid the singularity. So that's the quantity we need, and maybe we can just motivate it here. This is something that we're somewhat familiar with. Let's look at that quantity. And notice that this is, so as for x going to plus or minus infinity, then this whole thing basically goes to 0, right? Goes to 0. And for x going to 0, that's where we have the problem. That's why we shift this. We're getting infinity, and we're getting it as a complex function, right? So, but that's basically those are the values that we get in these limits, and so we sort of recognize this. It's sort of a complex function, delta function. So it reminds us of the delta function, and when you integrate the delta function, so we're sort of motivating some ideas here, being less rigorous. We're not going to go through all the derivations. When we integrate the delta function, I'll just write it like that, it just sort of picks out a quantity, the value of that function at that quantity. And so we're sort of motivating the following result that you get if you integrate this properly through the poles in the complex plane. In fact, we're motivating the limit as limit as epsilon goes to 0. My eraser is a mess. So epsilon goes to 0 of dx minus the plus infinity of e to the minus I xt over x plus I epsilon. We're motivating the idea that this gives us some constant. I think it's a negative constant, 2 pi or something like that. We're in it's a complex function. There's an imaginary number, and we get the step function. We get the value of the function of t, where theta of t is equal to, it's just 1 if this t is positive, and 0 if the t is negative. Those are the regimes that we're going to care about, positive values and negative values of that function. And that's going to be key, because we're going to end up with something like this that involves 2 different times, an earlier time and a later time. And that's where we're going to get the interpretation that we introduced earlier of particles and antiparticles.